with Brandon Hermalyn.
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 Yes.
Pardon me.
Okay. Got it. Okay, well, thank you so much for having me here today. It's always nice to talk about more dust around the moon, and the last two talks have really set up, I think, the stage really well for viewing the moon as in a sort of slightly different dusty environment where we're getting constantly bombarded by stuff. So I'm going to be talking about a different instrument that was on board LADEE, the UVS, the Ultraviolet and Visible Spectrometer. Oh, this is cool with the iPad. This is like the future here. So we don't have to go over this too much, of course. There's a couple of main sources for dust contributions to the exosphere. The biggest one that we're going to, I think, be considering here is impacts, right? And this can be broken into two separate categories, both steady-state micrometeoritic background impacts, but also individual larger events that should be happening perhaps more sporadically, but would be delivering a much larger amount of mass up to the exosphere. And then there's a whole bunch of other stuff, right, that we don't really know very well exactly how much this is contributing to the dust exosphere. We have electrostatic lofting, high energy radiation, UV or X-rays, interplay with the solar wind plasma, some other new things that I think were talked about earlier this week. But today I think we're going to talk about three main things: LADEE UVS measurements towards exospheric dust detection, which are mostly from lunar limb views, modeling of impact contributions, and some very preliminary looks at some of our data so far. So I hope that you guys caught Tony Colaprete's talk. I think it was 2 days ago. It was yesterday. Any of Tony Colaprete's talks actually would have helped this, but the LADEE UVS is an ultraviolet through visible spectrometer. It was on LADEE, and ours was a different type of instrument in that we were actually looking out. So it's not an in situ detector like LDEX we were just hearing about. So using the telescope, we have a very small field of view. We're able to look out over the lunar limb and integrate all along that field of view. So we should be actually quite sensitive to dust. So we had a couple of different viewing modes here, and I've sort of highlighted three of them. We have a sunrise. So, of course, LADEE is going around retrograde equatorial orbit. So as LADEE is going around this direction, we'll be able to look over the sunrise as we trail it, over sunset as we come into come out of umbra, and then also noon looks that occur over the middle of the moon. So just in case this is confusing, remember we're basically looking down from on top here. So I have a video which is supposed to play now, but I'm not sure if it is going to. Oh, this is cool. This is a quick animation just because I think it's sometimes a little bit difficult to understand what we're looking at. So LADEE is going to do a quick nod here over the terminator. The telescope will go up and then down very close to the surface and then back up. And then we will go into umbra as we continue to take measurements. It still has a video, and I can see myself on this, so that's cool. I like this. So I wanted to give you a quick example of some of the data that we're getting out of UVS. So in this particular mode, we're using UVS more as a really, really sensitive photometer than we are as a spectrometer. So if you look at the top plot here, this is dimensionless at this particular point, although we do have some radiance calibration that we've recently been able to get pretty close. But we'll look at as a function of time of, for example, this is a given activity. The intensity will go and sort of follow this blue line up here. I've highlighted the sunrise horizon to show that there's a pretty significant difference when we pass over from sunrise into umbra here. In the green, this is plotting the altitude of LADEE. Excuse me, I have to clear that up. This is plotting the altitude of the bore sight of our telescope at its lowest point over the lunar surface. So LADEE is going along at considerably higher, but we're pointing down a little bit here and trying to track this. This includes terrain effects, which are actually considerable effects. We come quite close to some of the larger mountains, especially later on in the mission. Down here, there's a couple other things we have to take into account here. This is a plot of some of our geometries. So on our, apologies if this doesn't come across very clear here. This is the telescope Earth elongation angle on the bottom. This is important because we do an excellent job of finding Earth anytime it comes very close to our field of view. Our solar elongation angle up here, and our telescope grays solar longitude on the surface of the moon. solar elongation, particularly during our searches for dust, we have to be very careful that we're not getting any scattering, or at least minimal scattering into the field of view. Solar influx is considerable signal, so we want to make sure that that's relatively minimized. We can also use it as a spectrometer. This is just a few color ratios here. This is blue to red, green to red over here, excuse me, and blue to green. And again, I have sunrise plotted along here as well. So we can also look for the very, very sensitive color temperature changes as we go through perhaps a dust cloud or anything else. So I want to take a couple of minutes to talk about the impacts, right? This is, I think, divided into two separate categories. At first, we're going to talk on this on the right-hand side of the slide, larger impacts. So this is where the projectile is much, much larger than the target grain size. This is not micrometeoritic, where a lot of those are coming down at the exact same size as our regolith grains. But these are also sporadic events, and so not just sporadic events, but also during meteor showers we can have larger events. But much, much more mass is delivered to the exosphere. And in fact, we highlighting I think there's an abstract from LPSC, where LROC has been noticing that there's a large number of these sporadic events that are occurring because we can see new craters formed. Now, on the other hand, we have a constant rain of small stuff where the projectile is about the same size as the target grain size. Now, the impact physics is rather different when we get down to the size scale. It's almost a bowling ball problem where or excuse me, a billiard ball problem. I guess if you have very large bowling balls, it also is a bowling ball problem. But it's where, as opposed to treating the surface as a continuum, and looking at the shock profile through that, if you have two particles that are about the same size and one hits the other at very high rates, it severely attenuates the shock profile. So you not only get less mass delivered up to altitude, but it also looks a little bit funny from a shock standpoint. We have a huge number of these, right? It's a constant rain, but minuscule mass is delivered, and this mesoscale problem, that's what I'm referring to where it's the billiard ball problem. So we took a little bit of time to do some impact ejecta modeling, which is a convolution of several different things. We have, impact angle, velocity, density, the field of view of the LADEE UVS, and also the location of our instrument bore site. So taking a bunch of impact models and some stuff that we did out at the gun range just down the street here, and convolving it with what we think we would have seen in the UVS data. So it's hard to generalize this overall impact angles, but we've applied to a nominal case here, and this is my animation of, or this isn't even an animation. This is our cartoon of what we're looking at. So as we come around the side of the moon, if we were to have a larger sporadic event, we would get essentially an inverted lampshade of ejecta, and we should be able to image through it kind of in this general geometry. Now, given the last couple of talks, we should be seeing this, right? We seem to be seeing. The LDEX team has been seeing a large number of these events, particularly during meteor showers. So in order to build up this model, we did some experiments, partly as an offshoot of a PG&G funded activity down here at the NASA Ames Vertical Gun Range. I think most people are familiar with this, but I'm uncomfortable presenting without having a slide in on this. We have a large vacuum chamber here. This blue thing down here is about 2 meters tall. And the gun itself is a two-stage light gas gun that's mounted on this orange A-frame. And the cool thing about the Ames gun range is that it's mounted on this A-frame and on a Nike missile screw, which you can see here is this black thing. That allows the gun to come up and over and pivot and shoot into say, a granular material at different impact angles at relatively high rates of speed. We can go up to about 6 kilometers a second with this, depending on the size of the projectile. So from a data standpoint, I don't want to go too much into these plots here, but I have two plots that are the velocity of ejecta, which is scaled, versus time after impact. And this is the ejection angle of ejecta, also as a function of time after impact. And I'll draw your attention that this is a log-log plot, while this is a semi-log plot only along the abscissa. The takeaway from this, I think, is that and we have two different materials on here, which is the canonical sand target, and also a lunar regolith analog. And our best lunar regolith analog is not JSC1A or any of those actual analogs, but it's airfall pumice dust And this is highly agglutinitic stuff, not stuff that you take from the block and chop it up. It's this dust that, as it falls down, is a glass, and it forms these shards that are not only highly agglutinitic, but they have these high angles of repose, exhibit the same sort of shear strength under tension. So it's so far our best way of making craters that look a lot like lunar craters, and it's been validated actually quite well with our L-cross impact experiment. You'll notice that the velocities of these two different materials are very, very similar. However, the ejection angles are rather dissimilar. We have almost a 10-degree difference in ejection angle as a function of time, and this is our airflow pumice regolith analog that's coming down here. It's actually coming out relatively low and starting to rise up later. Now, for the stuff that we'd be interested in seeing, thank you, I'm almost there, we'd be restricted to this very, very early time regime for both of these, because all the rest of the stuff is traveling too slowly, would never get into the field of view. You'd never see it. So we convolved this with some ejecta mass measurements that we've been making at the gun range. I'll ignore that and have a quick video just to visualize actually what we were hoping to see with the LADEE UVS. So the concept here is LADEE's over here, and we're looking into an ejecta cloud, and you can see that this green area is the projected field of view through the ejecta cloud. So this takes into account all the different impact ejection angles and the velocities and the masses. And taking all that into account, if we could move past the video, I have to do this, right? Okay, thank you. We're able to come up with some estimates. So this is for a 1-meter crater. We were assuming half-micron particles. And for that particular impact, if we get lucky and we're looking at the right place on the moon and we see this impact event happen right in the middle of our field of view, we see something on the order of 2 times 10 to the minus 5 grams in our field of view. We should be able to see that with our instrument. So with this is a 1-meter crater. If you have a larger crater, of course, you would see more. Or if you have different size particles, you'd be able to see more. But I'll stress again, this is if we're lucky. This is a sporadic event. If we see it in our field of view, we have to be on all that. So our takeaway 1 here is a number of events actually should have been visible statistically in our LADEE UVS data set. We do have to get lucky to be on at the right time in the right place to see them. Those that are not visible will contribute to the orbital debris that are lasting for hours. So we should be able to perhaps see some sort of influx that is increased for hours after an impact event. Because remember, this stuff is traveling maybe not at escape velocity, but real close to it. So it's on a Keplerian orbit that can last for hours. It's also one point here extremely important to rule out other scattering effects for not only Earth, but sunlight scattering off peaks and possibly near our field of view before making any definitive statements on how many impacts we've seen, which is why I haven't said that yet. So real quick, I think I have a couple of minutes. Just want to go very briefly. No. Oh, okay. Well, very briefly then. We have a couple of things. I just want to be left with this sort of big data slide here. Looking at this as a function of solar longitude, these are all of, I plotted up for just about a month's worth of data. These are all of our tracks over the sunset, the noon, and the sunrise horizons. And this is essentially the flux into our instrument. And what we see, if I just want to examine this last slide I've made here, which is that if you look over all of these, just at the sunset terminator, for example, and you align them with some of our meteor showers that occurred during this time, you definitely see some structure in our data, which is that at some points we have, in general, lower flux. Sometimes they correspond to meteor shower events. We have higher fluxes as we come around the sunset terminator, and over here again. But sometimes we have much higher signal that does not appear to be correlated with any of our meteor showers that we had yet discovered. So with that, I'd like to say thank you for your time and ask if you have any questions. Thank you.
Time for a few questions. No questions? Then thank the speaker again.